Okay, so at the end of the last lecture, we had presented a model of a field, which was a set of masses connected with springs. We said we'll do a subset. Okay, now is the opportunity to do it. So we have a series of masses, all equivalent, sitting at the same distance one from the other, and connected by springs. Okay, each spring has a constant, let's call it Ks. Why Ks and not simply K? From the simple reasons that we'll do a Fourier transform at one point or other, and we don't want to confuse them. The distance between all masses is A at equilibrium. And of course, at any given time, they can move. So let's call the position of the first mass R1, R2, R3. And so on. Great. What will be the Hamiltonian of the thing? Classically, let's assume that we have n masses. Where P is the momentum, and we assume all masses are equal, therefore it's n. The distance between two masses, when I'm taking into account that there's equilibrium at a distance of A. Okay, trivial. We've seen it many times. If instead of using Hamiltonians, I would like to use Lagrangians, and for different reasons in field theory, sometimes, most of the times even, Lagrangian is more useful than the Hamiltonian. So, also no problem. Where T is a kinetic energy, U potential, and just in the same way, okay, again, trivial. Now let's use the fact that we have an equilibrium here and assume that the masses in this chain don't move much beyond the equilibrium, and rewrite for each mass we have the equilibrium point, which is the lattice point of this one-dimensional system, and it's moving by an amount phi L, which we assume is much smaller than the distance between the masses. And I'm writing myself T to remind myself that, of course, it might depend on time. Okay. Yes, please.
Can you please explain again the RL?
Let's. Okay. Where is the second mass? Let's say. If I measure from the beginning, A plus A, 2A, right? Right? But this is not a frozen chain. If it's frozen, nothing interesting happens. So how much it's moving from the equilibrium point? This is the speed. I'm calling it a Greek letter just because it will be used as a field letter. That's the usual notation for it. But nothing really clever here. All it tells me, you're at equilibrium and moved by a bit from equilibrium. And for each mass, 1, 2, 3, 4, you're moved by some amount, which doesn't have to be equal, right? Once I have a list of all these values, I know exactly where is the. Well, I'm not here. I don't know about you. Okay. Now the only things I'm missing here boundary conditions. So usually in this game and during all the course, if I have no special reason not to use it, I'll use cyclic boundary condition, meaning basically, if you want, it's closed. Okay. The big brother is calling us. Okay, marvels of technology. Okay, so the momentum is just n times the derivative of r, but that's constant. Therefore, that's the derivatives, and let's write the Lagrangian. Just substituting the values of RL here. Till now, everything that we did is completely trivial. Okay. What happens when we're considering a continuum? Until now, everything is discrete here. Okay, my index L becomes the position X. The series of variables that I had previously that told me I'm moving at each point 1, 2, 3, 4, whatever distance from equilibrium, becomes a function that tells me at each point x how much I move. Okay. Instead of a summation, I have integration. And the only thing I have to be a bit careful about is units. Well, okay. Okay, so previously I was not concerned with units, so I wrote what's written here. Now I'm a bit more careful, but it's the same idea, basically. Now I will introduce a new idea, which is basically the Lagrangian density. And this actually, so I'm rewriting this for a continuum. I have all the building blocks. I have summation. I have the field. So this curly L is a Lagrangian density. F is a functional. Do I need to explain what is a functional? Right. And for the case that we have discussed here, taking the definition we wrote previously, so I took the simple case that I can understand very easily, intuitively, what is the Lagrangian, the discrete limit, and I took it to continue. Actually, in this case, it's almost trivial. When we'll go into other problems with field theory, it always helps to look on the discrete limit. Somehow humans have better understanding of discrete systems than continuum. Okay, what can we do with this Lagrangian? Well, in the classical case,
Equation of motion.
excuse me, I want to get to an equation of motion. So in classical field theory, all I have to do integrate over time, meaning okay, we don't need the discrete limit anymore. And the most basic notion of classical mechanics tells me that this quantity, which is known as action, should be extremum. So, okay. This anymore?
Can you explain that last line you wrote? The delta S.
In a moment, I'll explain what is delta S. It's not an easy concept.
After the first equation, and on the top of it, it's a after the k, it's a on
Square.
exponent 3.
What?
3, not 2.
I had a summation there. The summation became an integral, 1 over a. A to the third divided by a is a squared. That's why I defined it in this funny way. The a to the power half of the field. So I'll be consistent. Okay, so what's the differential of a functional? So I'm stepping one step behind and looking on the simpler case, somewhat simpler case, where I was considering a one particle system. For a single particle, What information did I have? X of t. We discussed it in the previous lecture. Basically, I put in some trajectory between t and t0 and some point, let's t1, t0, x0, x1. I have 2 points. And now what does it actually, this actually tells me to do? Go over all possible trajectories between that start at x0, t0 and end at x1, t1. Calculate the action, and you will find some trajectory, not necessarily straight, depends on the system, for which S is x2. Either smallest or largest. A whole interesting discussion in classical mechanics when it's maximum and when it's minimum. I don't want to get into it. Anyway, so basically, what do I have to do in order to calculate delta of S? I take some function, some value of x of t, so is this guy, and start to move it around. And get a different trajectory. And check if by doing these changes I got larger value of S, smaller value of S. Exactly the same logic that stands behind the derivative, a usual derivative of a function. Just from the point of view of doing the calculation, this is more complicated because you have to check not moving a point, you have to move a point at each t. Okay, so let's try writing it up. So again, I have this notion of infinitesimal change. So I take an epsilon and take it to 0. What does it tell me? Okay, I'm going on this guy, changing it at some point from x to x plus epsilon y. Doing it all along, subtracting. and seeing whether what result does it give me. Yes.
What is y? Isn't it supposed to be x plus epsilon x?
I don't want to. It's a bit more complicated because I'm allowed to choose the functions that I deform with. I have a function and I'm deforming it by something. Okay, so I'm controlling the fact that it's small by this epsilon, but why I'm not restricted. Then you have all kinds of ways to do it systematically. Let's say take something that's always standing in 90 degrees to perpendicular to function or something like that. But in principle, I can just throw in a whole bunch of functions and see how it changes. Okay. So let's take this formulation just as an exercise. That's a result that you are well acquainted with. I'm doing just to get some feeling about this formulation. So taking a very simple formulation of the Lagrangian of a single particle depends on x and derivative of x. So instead of using y, I'll use your eta not to confuse ourselves with y may confuse us with x. So I'm doing exactly what's written here. Okay, just wherever I had x, I'm writing x plus eta, epsilon eta. Derivative of x, epsilon doesn't depend on time, eta could depend on time. Therefore, I have a derivative of eta.
And the integral is from 0 to t.
T. Good. Now I have to subtract them from one another. You know what? I'll do another step here. Epsilon is small. Until now, I didn't do anything with it. To zero order in epsilon, I'm returning just the change in the Lagrangian if I'm changing x, the change in the Lagrangian if I'm changing the derivative of x times the change. Everything else is a power of e squared. I don't care about it. Because e is going to 0 and I'm keeping going with the first. Subtracted divided by epsilon, so this falls off. These two are what I'm left with, divided by epsilon. And ending up with what's written here. Okay. Okay. What did I do here? Integration by parts. On this term, here I didn't touch it, here integration by parts. Because of the boundaries, remember that I always start with some x and t and finish it with some other x and t. So basically, at the boundaries that I can't deform the trajectory anymore. Is this understood? Don't be shy, say no. Okay, fine. Start from x0, t0. I end at x1, t1. Right? That's how I define my problem. I ask, what is the action on any trajectory that starts here and ends here. In between, I have the freedom to deform the trajectory in whatever way I feel like. It's perhaps not the minimum trajectory, but it's certainly a trajectory. But at this and this point, the boundaries of the integral, I have to start and end at the same point. So I have no freedom in the boundaries, meaning the deformation at the boundaries has to be zero. So therefore, I don't have additional terms here when I'm doing integration by parts. That's one of the basic ideas that I have in analytic mechanics. Okay. And this must be equal 0. This has to be equal 0. This has to be equal 0. And this guy has a name. Do you remember? Euler-Lagrange. Well, I can go through this whole exercise and do a very similar game and get the Euler-Lagrange equation, the motion equations for a field. Now, my feeling is that some of you won't be fully versed in doing all of the mathematical steps. So there are two solutions. One is just believe me that it's the same procedure. I'll write it down. It's the same procedure for fields. The second, next week, the tutorial will go over the mathematical steps. Okay, so since at the end of the day you're here in a physics course, not a mathematics course. So, yes.
You wanted to say that instead of Lagrangian, to use the Lagrangian density.
Right. Exactly that, and I'll just write the beginning and the end, and as hopefully you'll go through the tutorial next week on the intermediate steps. Okay. So instead of one number that depended on t, I have now a whole series of functions that depend on t. I have my Lagrangian density. That depends on phi.
spatial derivative should be squared.
Thank you. And here we add some field, the same logic that we did previously. Yes.
Why is it? Shouldn't it be m plus the time derivative? No, in the last, yeah. Or shouldn't it be because the squared?
I have to, first I take the time derivative and then I square it.
But you take the time derivative of all the parentheses.
Okay,
What?
I'm taking,
Okay.
so I'm just, instead of phi, I'm doing the time derivative, squaring it. It's not the second, if it was, what in mathematical notation, if I meant here the second derivative, would have been two dots, not dot squared.
Yeah, right.
Okay. Same games that I did previously, subtracting one from the other and calculating delta S. The only, okay, I'll do the intermediates. Term E square I don't care about.
Shouldn't it be big dot
Just
swell?
a moment. Yes.
Big dot swell? Big. The other one.
The
Yeah.
first one.
The first one.
Subtract integration in parts, the same game that I did previously. And I end up with Now, again, the start and the end, the boundary conditions force you that these terms are equal to 0, and I end up with and we have our Euler here it's actually second derivative, but that was because we did integration by parts. Okay. Question still here? Well, all of this still we didn't get to the title of the course, Advanced Quantum Mechanics. All that was fields, but classical fields. One more step before we're actually starting to do quantum mechanics on these things. Until now, all you did in quantum mechanics is Hamiltonians. not Lagrangians. Okay, so let's just write the field, the Hamiltonian of the field. As I said, when the course progresses, we'll also use the Lagrangian, but now just so you have something familiar, I'll write down the Hamiltonian. This. For a single particle, what was the momentum?
Should be conserved.
Excuse me?
Current. Should be conserved current.
Okay, let's not jump ahead. Just
Derivative
derivative of the position, and in the Lagrangian formulation, it's okay. Same structure. I take the Lagrangian, take derivative instead of according to x, x dot, I'm taking the derivative here according to phi. So the Hamiltonian, same definition, which would be a function of phi. Phi. So for our case, the Lagrangian was m over 2 pi dot square Someone can tell me what's psi?
It's square.
As usual. Thank you. And find out what. And since we're ending up with here, sorry, I wrote it as integrals as that's h. Okay, so we have the Hamiltonian. Lovely. Okay, as I said, until here, everything was classical. Let's go back to the discrete one, the discrete case. If I wanted for the discrete case to change gears and switch from classical physics to quantum physics, what do I do?
Need to add the אפשרות to create and destroy pattern.
Oh, that's 4 steps ahead.
Yes,
Simpler. You had a class for a single particle problem. You're well versed. You did 2 semesters of quantum mechanics. Someone gives you a classical Hamiltonian. What do you do?
No operators instead of
That's all. Instead of writing x and p, I'm writing x operator and p operator. That's all I do. So, if I take the discrete Hamiltonian that I've written in the beginning of today's lecture, all I do to quantize it okay, in a single particle problem, I had two operators, x and p. Here I have two n operators, p1, p2, p3, and so on till n, r1, r2, r3 till n. And what do I need to know about them?
Mutation relation.
Exactly all I need to know about them is a commutation relation. If P and R belong to the same mass, to the same point, there is a commutation relation. If P and R are on different masses, different particles, can measure them both, no problem, no commutation. And at that point, I'm finished. I have to calculate something, but from the point of view of quantization, I'm finished. Amazingly similar. Take my Hamiltonian. Turn them into operators. What does it mean, turn them into operators? Basically, the continuum limit of what's written here. Kronecker delta becomes Dirac's delta, and that's it. Okay. So what do we do in classical physics usually? If I had here a Hamiltonian of a single particle, what would
Find the
I?
eigen.
I would find the eigenvectors and eigenvalues of H. Basically, the same here. Okay. How do I even start here? Okay, let's do today's the first step. Well, you have enough experience still here to know if I don't know to do something in real space, what do I go and do?
Fourier space.
Transform to Fourier space. We'll do exactly the same game here. Okay. Just the regular definitions of Fourier transform. The only point that is worth paying attention, this was an integration, this is a summation.
You purposely switch the minus signs.
Yes.
With the
But it's my prerogative. I can define a Fourier transform as I wish. As long as I'm consistent, meaning if I'm doing the opposite to transform, change the sign. One conclusion that I can immediately take by by definition. And the final thing that I want to do now, what is the commutation relation between the Fourier transform of the operators for the commutation relation between pi k and phi k prime, just copy the definition. Okay, just copied the definition. Copied the commutation relation. Down here. Performing the integrations with delta functions are always fun. Giving us nice commutation relation. There's a commutation that is different than zero only if k is equal k prime. And to your question, why did I define it as once plus and once minus? To avoid here having k and minus k prime.
Doesn't really matter, but why it's not directive?
Why it's not directive? Well, actually, you should have asked this because k is discrete. Why is k discrete? And that's another reason why we're going over to k space and not doing it in real space. A finite region in X becomes discrete k's. Okay, because you can't put any mode, you have to have modes that end on the endpoint. And if you want, always going into, for a finite region in real space, going into momentum space turns your problem to both are still infinite, but one is countable and the second is not. So life is always nicer in momentum space. Okay, so basically we'll stop here, but what we'll do in the next lecture, take our Hamiltonian, which is written somewhere there, perform a Fourier transform, and see how to solve this Hamiltonian. Okay, questions? Good, so we're finished for today. At 6 you'll have the tutorial.
Thank you very much.
Thank you.